All right, in this screencast, we want to establish that side works, and we'll establish that angle side works. So basically what we're going to say is that triangle ABC and triangle DEF are rigged up such that AB is congruent to DE, BC is congruent to EF, and AC is congruent to DF. We're going to prove that the triangles are congruent. To prove that the triangles are congruent, we must prove that there is an isometry such that the image of A is D, the image of B is E, the image of C is F. That's the goal. So some language. There exists an isometry such that the image of A is D, the image of B is E, and the image of C is in the opposite half plane bounded by line DE as F. This is because AB is equal to DE. In other words, we're going to pick this triangle up and we're going to bring it over here, and we're going to force A prime to be here, and we're going to force B prime to be here, and we're going to rig it up so that C prime is in the opposite half plane bounded by DE as F. Because if they're in the same half plane, then it's hard to say, oh yeah, C prime has to be F. That's hard. So we put C prime in the other half plane, and then we do a reflection and we get the job done. Consider the reflection in line DE of triangle DEC prime. So the goal is to show that when C prime is reflected in line DE, it lands on F. That's the goal. We remember that those are the congruences. And so notice that E, F, D, C prime is a kite. Two congruent sides, two consecutive congruent sides, two consecutive congruent sides. EF, D, C prime is a kite. So DE is a symmetry line for EFDC prime. Because the line ED is a symmetry line for the kite, thus C double prime is F. Because that's what symmetry lines do. You remember from when you were 12 that on a symmetry line, we fold over a symmetry line and this piece matches up with that piece. Therefore, it's slowing down too badly. Therefore, there exists an isometry. Remember, it's a composition of isometries is an isometry. So there exists an isometry such that there exists an isometry T such that the image of A is D, the image of B is E, and the image of C is F. Thus, triangle ABC is congruent to triangle DEF, and we're done. This is how transformation-based proofs go. We find a transformation that puts one on top of the other. We can play the same game with angle, angle, side, congruence. We can have triangle ABC and triangle DEF, and we can get angle, angle, side, angle, angle, side, and the goal is to show that the two are congruent. And so in a similar way, there exists an isometry such that the image of A is D, the image of B is E, and the image of C lies in the opposite half plane bounded by line DE as F. So in other words, we do the same thing we did before. Because this segment is congruent to that one, we can put the image of A here and the image of B here. We know that isometries preserve distance, so we know that this is okay, and we put C prime in the opposite half plane bounded by DE as F. So then this is congruent, and this is like so. That's the picture. So now we consider the reflection in line DE of triangle DEC prime. What is it? How do we show that C prime lands on F? Then we're done. So we know by the angle bisector theorem, the angle bisector theorem that we talked about in the previous video, DE is the angle bisector of angle C prime DF. When we reflect this ray, this red ray, the image of that has to be ray DF. When we reflect this ray, it becomes this ray. So then the question becomes, where is C double prime? Does C double prime have to fall between D and F? Does C double prime fall outside of DF? Or is C double prime F? So, I mean, obviously we're going to get contradictions in two of those cases, we hope, right? So if C double prime is between D and F, then the picture looks like this. And if the picture looks like this, then angle E C double prime D is an exterior angle to triangle E F C double prime, and that's a violation of the exterior angle theorem because you've got an exterior angle that's congruent to one of the remote interior angles. So this is a contradiction. Well, it leads to a contradiction. If C double prime is on ray DF but not on segment DF, then your picture looks like this. Angle EC double prime D is congruent to angles EC prime D because reflections preserve angle measure. But You've got angle EFD as an exterior angle to triangle EC double prime F, and an exterior angle that's congruent to a remote interior angle. This leads to a contradiction. So this can happen and this can happen, and so C double prime must be F, and therefore there is an isometry T such that T of A is D and T of B is E and T of C is F, and therefore triangle ABC is congruent to triangle DEF. These are things that are important for us to have handy. This is the language you want to use when you're proving triangles congruent in a transformational way. Awesome. Hope this helps.